My previous video on quantum computation introduced many quantum gates and how they are implemented. This video uses many concepts introduced there, so if you haven't watched it or are unsure on what the Hadamard gate is, I suggest you check it out. In this video, we'll cover how quantum computers actually solve some problems faster than classical computers by introducing and analyzing Deutsch's algorithm. I'll briefly introduce how to actually code this quantum algorithm using Qiskit at the end. Classical computers are incredibly fast at solving many problems. Machine learning, convolutional neural networks, AI, are all examples of highly intensive computational problems humanity has implemented classically. The paramount advantage that quantum computers might have is providing faster solutions to some computational problems. Time is, after all, a non-renewable resource. When we model computation in mathematical terms, we typically have a simple input-output process. Many computers, however, obey the query model of computation, where the entire input is not provided to the computation. Rather, the input is made available in the form of a function, which the computer accesses by making queries. In this sense, the input is kind of like Oracle at Delphi, who doesn't tell us everything and only answers specific questions. To visualize the query model, we can view the total input as consisting of many individual inputs. When the computation begins, it continuously calls for one input string at a time, storing all of them as a continuous querying. Then, it finally outputs the result based on every query it makes. We'll see soon an example of a problem in which classical computers need to perform multiple queries, whereas quantum computers access the entire input with a single query, thus doubling computation time. We are going to be working with binary strings, so let's define the Greek letter sigma as the binary alphabet for the sake of brevity. Any computational function can be defined as taking some n-length binary string and converting it into some m-length binary output. For example, if n equals 2 and m equals 1, the function takes strings that are 2 binary characters in length and outputs a string 1 character in length, a 0 or a 1. If n equals 3 and m equals 1, the input is 3 characters in length and the output remains 1 character in length. For quantum circuits, we define a quantum unitary query gate, as the figure suggests. Here we say that x and y are arbitrary length strings. What UF does is to echo the top input string x and XOR the function value f of x on the bottom input string y. We are going to be solving a problem in the special case that n equals 1. There are 4 such functions that perform a 1-bit to 1-bit computation. The first and last of these functions are constant, since the output remains constant regardless of the input. The middle 2 functions are balanced, since the number of 0 and 1s are equal. Deutsch's problem takes an input 1-bit to 1-bit function, and outputs 0 if f is constant, and 1 if f is balanced. In classical terminology, it computes the XOR of f of 0 with f of 1. This is the quantum circuit that solves Deutsch's problem. To analyze this algorithm, we will trace through the action of the circuit and identify the states of the qubits at 3 separate locations. The state initially starts with the computational basis states. If we define these states using column vector notation and implement the Hadamard matrix on them, we get the following vectors. These become a lot more clear going back to Dirac notation. To visualize one more time how the Hadamard gate transforms the input states, let's go back to the Bloch sphere. As I said in the previous video, the Hadamard gate can be understood as first a rotation about the y-axis by 90 degrees, followed by a 180-degree rotation about the x-axis. If we perform these rotations on 0, we get the same output, and likewise for 1. These two outputs from the Hadamard gate, provided the computational basis states as inputs, are given a special plus-minus notation. The pi1 vector defining f of 0, f of 1 is thus just these two vectors multiplied, which yields the following. Going to the next step in the algorithm, the new state has to go through the quantum oracle. As shown before, this oracle XORs the function value f of x on the bottom input string, which yields the following. If you do some neat algebra trickery, you can transform the state further. At this instance, you can see something really neat happen. Although the action of UF leaves the top/rightmost qubit alone and XORs the function value onto the bottom qubit, here we see that the state of the top qubit instead has changed, changing the plus into a minus, while the bottom state remains the same. It's still a minus. This phenomenon is known as phase kickback. We can then pull the factor of -1 outside the sum. Notice that in this expression, we have f of 0 XOR f of 1 in the exponent of 1, rather than f of 1 minus f of 0, since the value of the -1 factor only depends on whether the exponent is odd or even. And thus we get the two following inputs depending on whether f of 0 XOR f of 1 gives 0 or 1. Finally, moving on to the final Hadamard gate on the top qubit. We just changed the rightmost plus and minus into a 0 and a 1. If you perform the Hadamard rotations on the plus and minus vectors, you can verify this. And therefore, with probability 1, or the coefficient in front of the 0 and 1 squared, we can definitively determine whether the input function is constant or balanced, solving Dutch's problem. This algorithm is justifiably called Dutch's algorithm, solving the problem with just one query, rather than a classical computer's need for two. We can actually program this algorithm using Qiskit in Python. This small segment creates the four possible input functions. The function quantum circuit initializes the circuit with two input qubits. These later if statements implement not or C0 quantum gates that define each of the four initial state functions. F of 1 corresponds to 0, 0. F of 2 corresponds to 0, 1. F of 3 corresponds to 1, 0. And f of 4 corresponds to 1, 1. The first part of this next code segment actually builds Dutch's algorithm, placing the necessary Hadamard gates for each qubit. Finally, this last code segment actually performs the algorithm, outputting constant or balanced. So you're probably thinking to yourself, performing one query versus two queries is basically nothing for a computer. However, we have to start somewhere. In the next video, we'll see a way to extrapolate Dutch's problem across any number of inputs using Hadamard tensor products, while keeping the time complexity for a quantum computer constant. Thanks for watching.